This is the last lecture of this module. So, let us complete in the. So, today we have two parts. We consolidate all the results we have discussed so far in the last 4 lectures, and in the second part of this particular lecture we will try to discuss quickly about the non-homogeneous equation. So far we were discussing the homogeneous system, but at the end of it we will also discuss the non-homogeneous system today. So, to introduce that, we need a concept called, to consolidate results and write it in the form of theorems. We are going to write now whatever discussed in the form of theorem. We need to have the concept of generalized eigenvectors. So, generalized eigenvector. As you see, our whole trouble is that when there is an eigenvalue which is repeated, and if an eigenvalue is repeated with order m, and we may or may not get m eigenvectors. If we get that many number of eigenvectors corresponding to its algebraic multiplicity, then there is no problem, we can always diagonalize the matrix and we can write down the solution. So, the problem comes for any particular eigenvalue if its geometric multiplicity is strictly less than the algebraic multiplicity, then there will be a deficiency of eigenvectors to find a basis of Rn, so that the matrix can be diagonalized. So, in this scenario we introduce the concept of generalized eigenvector. So, what is called, so let lambda be an eigenvalue, with algebraic eigenvalue of A, which is an n by n matrix with algebraic multiplicity m. Okay. So, we call we say a vector v not equal to 0 is in Rn a generalized eigenvector, of lambda, rather generalized eigenvector for lambda if A minus lambda I power k of v equal to 0 for some k equal to say 2 to n. Of course, when k equal to 1 it is an eigenvector. So, we in a generalized eigenvector we include even the usual eigenvectors. So, for some k this should happen. When it happens for k equal to 1 it is an eigenvector. When it happens for higher k it is called a generalized eigenvector. So, we use it for both the normal eigenvectors and more generalized eigenvectors. So, there is some interesting results which you can say. For example, we start with an example before going to that. You will note example, most of the parts are exercises. Look at this matrix A is equal to 2 0 1 2. So, lambda 1 equal to lambda 2 is the eigenvalue with algebraic multiplicity 2, algebraic multiplicity 2. So, the exercise is that there exists only one eigenvector, and that eigenvector can be chosen to be independent. When I say that one eigenvector means one independent eigenvector. Of course, if you have an eigenvector, every multiple of that is also an eigenvector, but you do not have a thing, and can be taken to be say v1 equal to 0 1. You can prove that if v is an eigenvector, every eigenvector will be a multiple of that one. Now, prove that is easy. Any vector is a generalized eigenvector. prove that any vector V is a generalized eigenvector. Generalized eigenvector. This is because you can actually see that, because you can see that A minus 2i whole square is nothing but 0 matrix. You see, once it is a 0 matrix, for every vector it satisfies. So, you can, therefore, one can choose V 2 is equal to 1 0 as another, as an generalized eigenvector independent of V 1, you see, independent of V 1. So, you got a basis consisting of generalized eigenvectors, and this is the theme we are using it. So, I will give one more exercise here. Here itself, let me write. It is a similar thing. Solve the problem. Solve the problem in solve the initial value problem with A is equal to 1 0 0 1 minus 1 maybe 2 0 1 1 2 is the same thing. So, in fact we are going to write this, of course this exercise is valid after the description. This you can write it as of the form S plus n. We are going to say that what is S and what is the. So, you have to complete the problem. I will recall this problem again as an exercise later. So, there is an interesting lemma can be proved, which is trivial, which is not difficult. So, I will skip it, I will not prove it here, we do not have that kind of time, that much of time. Let E be a generalized eigenspace. A generalized eigenspace means an eigenspace corresponding to generalized eigenvectors of a particular lemma. Be a generalized eigenspace. Just like it is an eigenspace is the space spanned by the all the eigenvectors corresponding to a particular eigenvalue, like eigenspace of A. Then this is already we are discussed corresponding to an eigenvalue lambda. Then E is invariant under A. E is invariant under A. That is a quickly you can prove it. That is A of E contained in E. See, A will act on the elements. So, whenever you have something, if you take any point in E, it will remain there. So, this kind of things which we know about the eigenspace will also work for generalized eigenvalue. So, I will not prove the results here because I will not have time to prove it. So, because we want to complete something. With this we also yesterday wrote that every Rn can be decomposed into stable, unstable and all that, which are invariant subspaces under the flow, not under A. The flow is e power T A. So, the spaces Es, Eu and Ec which are invariant under the flow e power T A. That is what we have discussed yesterday. So, we will now let me complete all the theorems, but this is whatever I am writing is essentially we have discussed in the in detail 2 by 2 in more detail, and so let me complete for the sake of let me write down in the for the sake of completeness. So, I will do first I will write so in the form of theorem. So, I will write 3 theorems. The first 2 theorem are special cases of actually the second final theorem. So, it is a special case theorem 1. Suppose A has only real eigenvalue. I am not talking about its simplicity, it can have multiple eigenvalues, but I am saying that assume A has only real eigenvalues lambda 1 etc. lambda n, lambda 1 etc. lambda n according to its multiplicity. So, lambda 1 can be lambda 2 equal to lambda 3 there is a multiplicity according to its multiplicity, taken according to its multiplicity. Then the result what we have discussed so far, of course which requires a proof, we did not prove it everything, which is nothing but the part of Jordan decomposition. Then there exists a basis V1 etc. Vn of generalized eigenvectors, that is it, generalized eigenvectors of Rn. That means a basis consisting of generalized eigenvectors of Rn, and so you take the, so each V1 is a vector, put that vector as a column vector. So V1, so this is the first column, V2 is the second column etc. Vn, which is a matrix, and it is a matrix formed by the independent vectors, it will be invertible, is invertible. So you have a basis of generalized eigenvectors, and A has the form, that is what we are so far discussing. The given matrix will not be diagonalizable. If you want to have diagonalizable, you need a basis consisting of eigenvectors, but what we are getting is a basis consisting of generalized eigenvectors. So what it says that you can decompose A into two matrices in which S is diagonalizable and N is nilpotent. So you see, so you have the problem of computing e power A, but every matrix can be written as a sum of two matrices, one S which is diagonalizable, and for once it is diagonalizable you can compute it, and N is nilpotent, and again computing e power N is easy. And not only S plus N is nilable with, so it is diagonalizable means with this diagonal matrix. So it is diagonal, you see you have diagonal lambda 1 etc. lambda n. More the, and is not only that, S and N commute, that is very important, Ns, N nilpotent. So you have all the properties nilpotent, and hence you can compute e power A. Therefore, e power A Ta is nothing but e power Ts into e power Tn. So you can compute this one, and Ts can be, Ts is of the form P inverse of A. So you can write down this is P inverse of diagonal of e power T lambda j. So diagonal P, and e power Tn is, N will be a nilpotent of order some k, order k. So in that case you will have e power Tn will be of the form, this we computed yesterday, T power n etc. T power k minus 1 by k minus 1 factorial into n. So you see n power k minus 1 of course. So if you want to find a solution, so solution is x t is equal to e power Ta of x naught. So you see you have the complete solution, you can directly write down using this one. This is a matrix, it is x on x naught, you get that one. So you have to compute that one. So this is the case when A has only real eigenvalue. You can also write a theorem too. Suppose assume A has assume A is of order 2n by 2n. Instead of n I am taking even order, that is all. To assume that, because complex roots occur in pairs. So if I want to assume that A has only complex eigenvalues, its order has to be even, and has complex eigenvalues, has all complex eigenvalues. So it's this need not be the case. I told you as this is a special case, complex eigenvalues. Lambda j is of the form Aj plus Ibj, lambda j bar is equal to Aj minus Ibj, complex eigenvalue, Bj not equal to 0. Okay. Then there exists generalized eigenvectors, complex generalized eigenvectors, complex vectors W1j is equal to Uj plus Ivj, Wj bar is equal to Uj minus Ivj. Okay, that one. So that if you write down, you can write in order means V1 U1, V2 U2, you write that way, real and complex parts, complex and real parts, Vn Un is a basis of R2n. So, we are working with 2n is a basis of R2n. So, write your matrix P is this matrix, P is a column now, V1 V1, these are all column vectors in Rn, Vn Un. So, it is a 2n by 2n thing, is invertible. Again further you have the same representation, the only thing is that is a complex. Further you have A is equal to S plus n, S is diagonalizable, that means P inverse of S P is equal to, you get diagonal of lambda 1. So, it is a diagonal, yeah, is diagonal. So, let me write is diagonal. Of course, diagonal entries with lambda 1 bar, lambda 2 bar, etc. is diagonal, n nilpotent, yeah, there is something to be, something is wrong, not exactly what I say. It is diagonal, is block diagonal, it is block diagonal. What is the meaning of block diagonal? I am telling, this is of the form, you will have diagonal of each block, block will have 2 by 2 entry, Aj minus Bj, Bj, Aj, sorry. So, that is the block diagonal. So, that is the correct way of writing. P inverse of St is block diagonal. So, the first D which we have seen yesterday. So, the first entry is first block 2 by 2 and then 2 by 2, then 2 by 2 like that along the diagonal. So, it is 2 by n and n nilpotent of course of some order nilpotent. Yeah, that is it. Sn equal to S ns, this always you need it to commute, then only you can compute. So, you can again write, and we can write the solution as, again you see, we can write the solution as complete solution as xt is equal to P diagonal, because you can compute the e power of this one easily, that is nothing but e power, this we have already done for each one, cos bjt minus sin bjt, sin bjt, cos bjt, this is the diagonal entry, this is the e power of that one into p, and then you will have your e power tn. E power tn is nothing but I plus tn plus etc. t power k minus 1 n power k minus 1 by k minus 1 factorial of x naught. So, you have the complete solution. So, you see, of course, this involves the interesting point to be remarked here is that to write down the solution even though this is diagonalization, this block diagonalization is done via the finding the generalized eigenvectors, at the end you do not need the generalized eigenvectors to be computed. To write down the solution, it is enough to find the eigenvectors, all the eigenvectors and its order, algebraic multiple. You do not need anything further. So, you are, if this is the situation, you do not need to find the generalized eigenvector in these special cases. You see, that is the interesting point. So, now we will write the last part of it before going to the non-linear. So, the general case which you are already seen, this is nothing but your Jordan canonical form, which we have already written yesterday. Today we have written the special cases separately, that is all. What it says that, so you start with, I do not write it in the form, so this is a theorem again, you can write it if you want it in the form of the theorem. Let A be of order, to separate of order k plus 2n. Now, this does not reduce any generality, this is just to separate your real eigenvalues and complex eigenvalues. Here I am going to assume that it has lambda 1 etc. Lambda k real eigenvalues. So, you can have any number, any n you can decompose in the form k plus 2n real eigenvalues. Lambda k plus j is something like or lambda j itself, you can write it lambda j equal to aj plus ibj, lambda j bar is equal to aj minus ibj, bj not equal to 0, it is a complex eigenvalue and j runs from k plus 1 to k plus n. So, you see, so you have all the eigenvalues and then there exists basis, that is all it is, there exists basis, we do not write it, of generalized eigenvectors, you see, you can write your complete theorem and you can write down your P. So, you will have P, you write your P as the matrix. So, you have the first k eigenvectors, generalized eigenvectors corresponding to k, this is not here, corresponding to the real eigenvalues. So, this V1 to Vk is the eigenvectors, generalized eigenvectors corresponding to lambda 1 to lambda k, and then V1 U1 Vk plus 1 Uk plus 1 like that to Vk plus n Uk plus n is the are the eigenvectors, generalized eigenvectors corresponding to the complex eigenvalues, and this matrix is invertible. So, you considering what the most general case, and A, and with this P you cannot diagonalize, you can write down the diagonal with the blocks. Now, you will have the problem, earlier you had a very particular format in the specific cases, but you will have diagonal of B1 etc. For some R, we do not know, that are all depend on its multiplicity and algebraic multiplicity, geometric multiplicity, various factors, where each Bi is a block, where each Bi is a block. Block maybe can be a 1 by 1 block also. So, if you have only one simple eigenvalue with one vector, it will be a single one lambda, it will come, and it takes one specific form and takes the form, that is a thing, and takes the form, and this we have computed already, yesterday we have elaborate way computed, and any Bij will be of the form lambda etc. lambda, and the upper diagonal elements 1 etc. 1, the rest of the elements are 0, and the order again depends on the multiplicity. There are some estimates for that, we will not discuss here, but any typical Bj will look like this particular form, and the order of Bj may vary depending on the lambda j's. This is for the case if lambda real, or it can have the block, or so it can have the block Bj will be of the form again we have discussed how to compute the one. This will be d I2 d on the diagonal I2 here d I2. These are all 2 by 2 matrices inside, where d is equal to of the form, d will be of the form A minus B, B A, for if lambda is equal to A plus IB, B not equal to 0, and I2 will be of the form is the identity matrix 2 by 2 identity. So, this is the typical eigenvalue. So, using this will immediately write down your solution as x t, because so you have decoupled system Ax equal to x dot equal to Ax. It is enough to solve the system for y dot is equal to Bj of y. For each Bj you solve it separately, and each Bj will have one of either this form or this form. So, with that you can immediately write your solution x of t is equal to, so let me finish in this page itself. You will have p, since this is of the diagonal form, even for the block the diagonal form works. Okay. So, it will be of the form diagonal e power t bj db1 etc. e power t br at p inverse of x naught. So, you see, so you have your complete solution. So, you have that. So, and how to compute t power bj? Each t power bj is a matrix, submatrix which is the same order as the bj, and how to compute t power tj is what we had discussed yesterday. So, this gives you the complete analysis of the Jordan composition and representation of the solution for the linear system. So, with this we now move on to the last section of this talk, namely for the non-homogeneous system. So, we will move on to the next section, non-homogeneous equation. Homogeneous, again autonomous. We are in autonomous only, because all these facilities are available. No. So, what would be your equation? You have your equation x dot t is equal to A, which is independent of t. So, x t plus g t, where A, the elements g t. So, you can have your g t and your initial condition x at t naught is equal to x naught. Okay. So, we are going to introduce a concept, two concepts called fundamental matrix and transition matrix. This is crucial even in understanding. I mean, you can write down the solution in a without introducing these notions, which I am going to describe soon, but that is the thing used to understand non-autonomous systems, because this represents. So, we are going to represent the solution of this system in a using the fundamental matrices, which can be generalized to the non-autonomous system. So, let me introduce this notation, which is crucial: fundamental matrix and transition matrix. So, let me solve this system is the system 2, let me call it, and we call it the same notation I am using. I am not using in a different notation. I am using this notation A for even for the homogeneous system. So, this let me call it 1. This is my 1, and so so I want to solve this equation with x at 0 is equal to say x naught. I can solve for various initial conditions. So, choose x naught equal to the basis vector E I here, where E1 to En canonical basis, canonical, that is 1 0 etc. of basis of R. So, for each of these initial condition I will have a solution, and let phi I t be the solution of 2, be the solution of 2, solution of 1. I am talking about the homogeneous equation, that means phi I t satisfies the equation 1 with that is phi I t at 0 will satisfies the equation E I, that is all. So, phi I dot is equal to A phi I and phi I 0 is equal to E I. So, with this I can introduce phi t, a matrix, because phi t is a vector, it is a vector solution. So, each vector I will put it in the first component phi 1 t etc. phi n t. You know that these are all independent solutions and invertibility. Now, you can you can immediately understand this equation. And what is this phi t will satisfy? So, phi t will satisfy, each phi I t will satisfy an equation with 1 0 0 as the initial condition, phi 2 will satisfy with the initial condition 0 0 etc. So, phi t, which is a matrix, and satisfy the matrix differential equation, phi t, phi dot of t, phi is a matrix now. So, you can still that one it. So, you are arranging phi, your each row properly, and what is your phi at 0? Phi at 0 is nothing but identity, because phi at 0 is 1 0 0 etc. phi 2 at 0 is equal to 0 1 0 etc. It will satisfy the matrix differential equation. Okay. So, you can do it instead of the initial condition. I can do the initial condition, we can one can take the initial condition at t naught. So, but by the way, what is the solution of phi I t? Phi I t is nothing but e power t a E a, right. E I is the basis, the other E is the that is it, that is not a problem. And what is your phi t? Your phi t is nothing but arranged in columns, it is nothing but your flow, you see. So, phi t is not in this particular case. So, I can take your phi t naught. So, I introduce phi at t naught is nothing but phi at, these are all very special case, works for the autonomous system. This is nothing but e power t minus t naught of a, and this will again keep so this phi t naught again will satisfy your matrix differential equation, but with the initial condition at t naught. That is all the difference, we just translated satisfy the matrix differential equation, d by dt, that to avoid that t naught also there, which we are going to vary, phi t naught. So, nothing but a of phi t naught. T naught is fixed, t is varying with the initial condition at t naught, phi t naught is identity, you see, that is the thing. So, you have your solution, essentially I am translating a t naught. So, you can write down. This is called the transition matrix. The matrix definition, the matrix phi t t naught is called the transition matrix, because the name is suits transition. This is where what is it's happening is that it takes the point at t naught. If the position is at t naught is at x naught, it takes to phi t t naught of x naught at time t. Okay. So that is what happening. So phi t t naught of x naught is equal to, you look at that, phi t t naught of x naught is equal to x naught, and then at time t the solution will be at, so x at t is equal to phi t t naught of x naught. So you take the trajectory. So if you have the trajectory at the initial point, this takes to the trajectory translate. So the phi t t naught takes the trajectory from x naught to x t at time t. So the name is correct, the transition matrix is correct. Okay. This also have the other properties which we may probably tell a little later. We will try to say something later at the end of it. So there is also a notion of fundamental matrix. Okay. Fundamental matrix. It is more or less like a transition matrix, but we do not put a condition on the initial value. So any matrix C of t, that means consisting of functions. So the entries of side t are functions matrix satisfying the matrix differential equation, satisfying the matrix differential equation, psi dot of t is equal to a psi t is called a fundamental matrix. So the trivial fundamental matrices are transition matrices. So you see, so every transition matrix is a fundamental matrix. Every transition matrix is a fundamental matrix. So okay, and fundamental matrix in this particular situation is of the form e power t minus t naught into a. That is your thing, every transition. But there is also another interesting thing which you can easily prove. Suppose C is invertible, there is no, suppose C is a constant matrix, which is C is an invertible, of course constant matrix, invertible constant matrix. Then psi t, you define psi t as phi t, you post multiply C, then consider this one, consider psi t. So this implies psi dot of t with respect to t, phi t means phi t t naught, if you want to do that one. So I suppressed t naught here. Psi dot t is equal to phi dot of t, and C is independent of t, but phi dot of t is nothing but a phi t and C, and this is a associative law is true. So substitute phi t, that you will get a psi t. That means if you take any invertible matrix C and then define phi t is equal to psi t is equal to phi t C, then is also that implies psi t is a fundamental matrix. Okay. But the interesting result which is trivial to prove, so I will leave it as an exercise. Every fundamental matrix is of this form. Every fundamental matrix, given any fundamental matrix, C, there exists an invertible matrix C such that C t is of the form phi t into C. In fact, if you observe, you can compute C for given phi, given C you can given psi you can compute C. In fact, psi t naught is equal to phi t naught psi, but phi t naught is nothing but phi t t naught. I told you already the other one is suppressed, phi t t naught C, okay, is initial value. Phi t I represented for phi t t naught suppressed, but phi t t naught is identity. So this is nothing but C. So your C has to be of the form psi t naught. So you have that. This is a trivial exercise. With this you can compute and do that one. Psi is of the form, that one. You need the uniqueness of the solution, that is all. Now with this we will go to the non-homogeneous equation. I use this notation. As I said, you do not need all this, but it is introduced to understand the non-autonomous system, which we may not do that one. So now non-homogeneous system, we apply the variation of parameters which we have done in first and second order equation. We variation of parameters, okay. So note that if you see, so I use this notation phi, so let me work with that initial condition t equal to 0, that is enough. You can work with any t naught also. So choose t naught equal to 0, so to avoid, but you can, it does not matter, there is no loss of generality, okay, no loss of generality, only you have to work thing. So note that phi t is equal to e power T a of x naught for V satisfy the homogeneous equation, This is the same idea we have used homogeneous equation with phi at 0 is equal to V. So the idea which we have used in variation of parameters, if you take your flow e power T a and act on any constant vector V, it will only satisfy the homogeneous equation. So you can never expect to have a solution e power T a V for a non-homogeneous equation. So the idea which we have used is to vary V, V and view it as a function of t, That may give you a hope, because if you do not do that one, you are never going to get a homogeneous non-homogeneous solution. This might give. So assume phi t, assume x t is e power T a into V t is a solution of non-homogeneous equation, solution of x dot of t is equal to a x t plus gt. Now, let us compute here, compute. If you compute x dot of t, so it is a product formula. Once you apply the differentiation to the first term, you get a here, a e power t a v t, and if you apply that to there, you get e power t a into v dot of t. This is nothing but your e power t a into v t is nothing but your x t plus e power t a into v dot of t. So, if you want x dot is t is a solution to this non-homogeneous equation 2. So, if x t is a solution to 2, will immediately imply we need to choose this term is gt. We need to choose e power t a v dot of t is equal to gt, or otherwise you have the first order equation for v t. This is an integral calculus problem, you would have nothing to do it, it is a e power t a into gt. So, you just integrate, that will give you your v t at v at 0, v at 0 is equal to what do I get it, v at you want x naught, you want this to be at 0, you want that to be 0. So, you have yeah v at t naught b v at t naught, if you integrate t naught, if you do that one plus integral t naught to t, of course you can work with the t equal to 0 or not, you integrate that one e power minus s a into g of s ds. This is what you want to do. So, you get that. So, now you substitute this formula, you substitute v t in, where do you substitute? You substitute here. So, if you substitute v t there, what you will get is a substitute, what you get your x of t will be, so e power, so you can do a small computation which I will skip here, t minus t naught of a at x naught. Of course, when you choose t equal to t naught, it will be just x naught. Do the computation, substitute and do the computation, you get plus integral e power t naught to t e power t minus s. This is just a small computation, absolutely no difficulty, g of s ds. So, you have that formula. So, this is your formula for your solution using the variation of parameters, you see. So, when there is no g, this term will not be there, and you know that this is the solution to your homogeneous equation. So, the first one is exactly getting what you have seen in homogeneous equation. You have a if you recall your second order equation, you have a complementary function which is a solution to your homogeneous equation, we have seen that, and then you have a kind of particular integral, and that is what we have done here. So, let me write it in this form. So, this is of the form phi t, this is nothing but phi of t minus t naught x naught and symbol form plus integral t naught to t phi of t minus s g of s dx. This kind of representations are very important in applications. For example, the non-homogeneous term will appear in the control form. So, plenty of applications which you know, plenty of applications. for example GT may be a control, GT may act as a control. So, and it may say for example linear control, say linear control. We will not get into that one of the form. This is a GT is equal to some B of UT. You see, so you have that control form, that format. Okay. So we will not do that one, but it gives you an important thing. And another thing, interesting thing is that here you can also define this kind of solutions in the weak form and other kinds of thing. In ODE it is called the mild form, and which is also important in control theory, because you do not look for controls which are continuous, and when you do not have the continuity, this kind of weaker formulations of the representation of the solutions you can write it as thing. So we will not get into that, but what we have seen is that you can write down your solution consisting of two parts. One part is the solution corresponding to your homogeneous system, and in the last 4 lectures we were actually studying the homogeneous system completely. You are trying to understand this phi t minus t naught of x naught completely according to various form, how to compute that one. Once you compute, you also have a second term that corresponds to the non-homogeneous part. With this we more or less end our thing, but we make a slide or a just one or two comments about the non-autonomous system, and we will stop here. Non-autonomous system. You know that non-autonomous system works completely different. Even in the second order you have seen that one. When you have a equation with a constant coefficients in the second order equation, linear constant coefficient equation, you have a complete analysis how to represent the solution. But when you have an equation x double dot plus pt xt plus qt x dot and qt xt equal to 0 or yt or gt, then you have no, there are some methods, but in general finding two independent solutions is difficult. You have the solution structure, and here also we are going to give you representation. What you have seen even in the n by n system, you have a complete knowledge of the homogeneous system in terms of the exponential. That exponential representation is not possible. So you have a solution here of this form x dot t. So the variation of parameters with non-homogeneous is fine, but even with a t x t, so we are not going to do much on this. X t naught is equal to x, but what I want to, or the homogeneous counterpart, there will be a g t there. But the interesting point is that existence and uniqueness available, existence and uniqueness available by the same general theory which you have studied in our earlier module. So the if of course the elements in x and the component elements in AT are continuous, that minimum assumption of the continuity of the matrix AT is required, but existence and uniqueness available from the general theory, from the general theory. Now the concept of fundamental matrix and transition matrix can be introduced. That is the important thing. Concept of, you do not have now e power t a, and finding a solution at t naught you cannot translate. So that is also an important thing. You can, it is not possible you find the solution at x equal to 0 and then translate it, because of the non-autonomous system, which you will see in more elaborate way in nonlinear analysis. You cannot just translate find the solution at t naught equal to 0 and then translate like phi t minus t naught, and that is not available in this case. So you have to study, if you want to understand at t naught, you have to study directly at t naught. The facility of this kind of translations are not available, which you will see in nonlinear analysis. But the concept of fundamental and transition matrix can be introduced. That is the whole thing. Transition matrices can be introduced, that is the important thing, introduce. So, now you have to introduce, so let phi, now phi, this is important, now you have to write separately. You cannot write this is of the form phi t minus t naught, that is not the thing. So, t naught and it works differently, be the transition matrix of 1, means it satisfies this matrix differential equation, satisfies the satisfies phi dot, that is d by dt, this is a matrix, phi dot at t naught is equal to a t phi t naught and x at t naught is equal to identity. This can be introduced, the thing, and you can also introduce the fundamental matrix xi. What is the mean? This is a matrix psi t which satisfies the differential equation, and you have the same formula. You can also write your xi t will be the form, psi t has the form, all that results are true here. Psi t has the form psi t is equal to phi t c, you can do all that, and your solution will be, all that can be introduced exactly this way, but never write phi t t naught is equal to phi of t minus t naught equal to e power t minus t naught into a, and that portion is not available to you. The rest of the system you can introduce using the uniqueness phi I t and then put it as a column wise, and you can introduce everything phi t t naught form, and you can write down here, and your solution also can be written as x t. You may think that it is solved, but it is nothing is solved actually. We are only saying that phi t t naught is a solution of this matrix differential equation, or phi I t, each column is a solution of your differential equation with a thing, but how to solve that differential equation and how to find that is not given to you. In the earlier case you have a representation of e power t, so you have your phi of t naught of x naught, you see. So, you have your solution, that is all you can do it for the homogeneous equation, and this is called the transition matrix. And for the homogeneous non-homogeneous system, you have your solution x t is of the form phi of t, you have the component y, all this can be a thing x naught plus integral t naught to t phi of t t naught, you have to write this way, not phi t t naught of phi inverse of, I think this probably may be yes, if I think this may be yes, there may be some s, phi inverse of, no, this is t naught only, here s t naught phi t naught g s d s. So, you have a representation of that form. Okay. So, you have the thing. So, the last thing, phi has the group structure, phi has the last slide has the group structure, because this is due to the invertibility of the reversibility of your system. When you know the solution at t naught, you can also solve it for the past, but then there are, when you go to PDEs and other things, you may not be able to do it, and you will only get a semi group structure. So, what are the thing? You have phi t naught, this property is identity that you have it, and the other interesting property, this is the crucial property, phi t s and phi s t naught is nothing but phi of t t naught. This is the most crucial property of the semi group structure. It means that your solution is going from S to T and S to T naught n. So, you have, if you want to go from T naught to T, first you go from solution T naught to S, and then you can take an initial condition at S and then go to T. So, that means you can go from x T naught at time T naught here, you reach at time T S here, and then you go there. Instead of, you can go directly here. That is what it says, this semi group property tells. So, this immediately tells you that this is invertible. The implication is that phi t s, if I put phi t naught, in particular if I put s equal to t, I get no, s itself, and if I put s is equal to t, I will get phi t t, phi t, or maybe I have to do it some t naught properly, and you get identity. So, that you will get it as inverse of phi t s is equal to phi s t. You can prove all that. It's the same thing. If you want to see that s is equal to t naught identity, t t, yeah, I think that is correct. So, we will skip that. So, you have all that property. So, as far as the non-autonomous system is concerned, you have all the representation of the solution using transition matrix, but there is no way in general to determine transition matrix as in the autonomous system. But then there are some conditions under which this transition matrix can be computed in some form of the exponential using certain commutativity of that one. So, with this we will complete the module on linear systems, and you will see the use of this thing in the when we study the nonlinear systems and stability analysis. Thank you.